The moon is slowly leaving Earth, drifting away by a tiny amount every single year. It sounds like the beginning of a disaster, but this quiet retreat may be one of the reasons life on Earth has remained so stable for so long. Tonight, this journey moves through tides, time, and planetary balance to uncover why the moon's slow departure helps make Earth a habitable world. If this kind of calm space documentary is welcome here, please like the video and subscribe to the channel. Earth moves around the Sun as one planet among several, following a path within a broad system of worlds, smaller bodies, dust, gas, and light. Far beyond Earth, giant planets keep their own retinues of moons. Closer to the Sun, rocky planets travel with much smaller companions or with none at all. In that larger setting, the Earth and the Moon form an unusually intimate pair. The Moon is not large enough to rival Earth, yet it is large in relation to the planet it circles, and that proportion gives the pair a special character. Seen from farther out, they resemble a close planetary partnership, bound together while they journey around the Sun. Their shared motion is quiet and regular. Together they sweep through space at great speed. Yet from year to year the pattern remains calm and repeatable. The solar system occupies a small province of the Milky Way galaxy. The Sun is one star among hundreds of billions, and the Earth-Moon pair is only one small arrangement among the many arrangements that nature produces around stars. Even so, within the local architecture of the solar system, this pair stands out. Mercury has no moon. Venus has no moon. Mars has two very small moons, both dark and irregular in shape. The giant planets host many moons, but those systems are built around planets far larger than Earth, with immense gravitational reach and very different histories. Earth alone carries a single large moon that so clearly shares its story. This fact is visible in the sky, but also in the mathematics of motion and in the long geological record of the planet. Earth and Moon belong to the same system so deeply that they are often described together before either is described on its own. From a distant view, Earth appears as a bright world with water, cloud, rock and ice, turning steadily under sunlight. The Moon appears darker, airless and bare, marked by ancient impacts and wide plains of frozen volcanic rock. One world holds oceans and weather. The other has no global ocean, no rain, and no thick blanket of air. Yet distance makes their differences seem smaller than their connection. The Moon accompanies Earth through every season and every year. It keeps nearly the same face turned toward Earth because its spin and its orbit are locked together in a stable pattern called tidal locking, a condition in which one rotation matches one circuit. From far away, that steady geometry gives the pair a composed appearance, as though the Moon preserves its place beside Earth without strain. Their partnership has scale as well as grace. The Moon is much smaller than Earth, with about 1/4 of Earth's diameter, yet that is still very large for a moon relative to its planet. Because of that size, the common centre of motion of the pair, called the barycenter, does not sit at Earth's exact centre. It lies inside Earth, but away from the middle, and both bodies circle that shared point as they travel around the Sun. This follows directly from gravity and mass. Still, it gives the Earth-Moon pair a dynamic balance that differs from the balance of most other rocky planets. Even from the outer perspective of celestial mechanics, Earth is not simply carrying the Moon along. Both bodies participate in a mutual dance, unequal in mass but shared in motion. Around them lies a wider field of gravitational relationships. The Sun dominates the system and holds Earth and Moon in their yearly path. The other planets exert weaker influences, enough to produce subtle changes over long spans of time but not enough to break the pair apart. The Moon therefore belongs to Earth, yet both belong more fundamentally to the Sun. This layered order is common in astronomy. Small systems live inside larger systems. A moon circles a planet circles a star circles the centre of a galaxy. The Earth-Moon pair reflects that nesting of motions with unusual clarity. It is local and intimate, yet never separate from the greater structure around it. This larger setting helps explain why the pair matters. A moon is not merely an ornament in orbit, it is part of the physical character of a planetary system. Some moons are tiny remnants, too small to alter much beyond their immediate surroundings. Some are active worlds in their own right, shaped by heat, gravity, and chemistry. Earth's moon occupies another category. It is dry, silent, and geologically quiet today. Yet its presence changes the long-term condition of Earth. From the outer view, before any detail of tides or climate enters the story, the basic fact is already visible. Earth is not alone in its path. It travels with a substantial companion, and that companion remains close enough, massive enough, and regular enough to matter over immense spans of time. The sky preserves this relationship in a way that few planetary systems reveal so plainly. The Moon appears large in Earth's sky because it is genuinely close in cosmic terms. It is far enough to be distinct, yet near enough to dominate the night. Sunlight reflected from its surface has guided living creatures, marked calendars, shaped observation, and provided one of the clearest visible signs that Earth belongs to a wider mechanical order. At the same time, Earth would also appear prominent from the lunar surface. It would hang in the black sky as a far larger disk than the Moon presents to Earth, striped with cloud and ocean, changing with light but fixed in place for an observer standing on the near side. Among all known worlds in the solar system, this reciprocity is one reason the Earth-Moon system draws such attention. The pair is neither symmetrical nor equal, yet neither is it trivial. The Moon is large enough to count, close enough to act, and steady enough to endure. Its orbit is not a random arrangement. Its presence is not a passing accident on the timescale of human life, or even the timescale of civilizations. Earth carries this companion through the darkness between planets, and together they maintain a long physical association that shapes the identity of both bodies. The wider solar system contains many wonders more massive, hotter, colder, faster, and stranger, yet few relationships within it are as quietly consequential as this one. From the broadest vantage, before attention settles on distance or gravity, the first truth is simply that Earth lives as part of a pair, and that pair moves through space in lasting company. The Moon circles Earth along a path that is both familiar and subtle. From night to night it changes position against the stars, rises at different times, and presents a shifting pattern of light and shadow. Yet beneath those visible changes lies a precise orbital motion. The Moon does not wander loosely through the sky. It follows a stable course around Earth while the Earth-Moon pair continues around the Sun. That course is not a perfect circle. It is slightly elongated, which means the Moon sometimes comes a little closer to Earth and sometimes moves a little farther away. Even this simple fact gives the orbit a living character. The path repeats, but it does not look flat or frozen. It breathes inward and outward by a modest amount as the Moon continues its steady revolution. On average, the Moon lies about 384,400 kilometers from Earth. That is the mean center-to-center distance, a useful measure for describing the orbit as a whole. In practice, The actual distance changes throughout each cycle because of the orbit's slight oval shape. At its nearer point, called perigee, the Moon is noticeably closer. At its farther point, called apogee, it is noticeably more distant. The difference is large enough to affect the Moon's apparent size in the sky, though the eye often treats each full moon as the same. These changes do not mean the orbit is unstable. They are part of the ordinary geometry of an elliptical path, the shape followed by many natural bodies under gravity. The Moon also moves with regular speed around Earth, but that speed is not identical at every point. When it is nearer, it travels a little faster. When it is farther away, it travels a little more slowly. This is a normal consequence of orbital motion. A body in an elongated orbit does not spend equal time covering equal arcs of its path. The Moon, therefore, sweeps through nearby space with slight changes in pace, while preserving the larger regularity of its month-long revolution. Measured against the fixed stars, one complete orbit takes a little more than 27 days, measured from one phase cycle to the next. The interval is longer, about 29½ days, because Earth itself keeps moving around the Sun during that time. These two ways of measuring the same motion are both correct. One describes the Moon relative to the distant background of space, and the other describes it relative to the shifting line between Earth, Moon, and Sun. Its orbital plane is tilted as well. The Moon does not travel exactly in the same plane in which Earth circles the Sun. Instead, its orbit is inclined by a little more than 5 degrees. That small tilt matters. It means the Moon usually passes a little above or a little below the exact line required for a solar or lunar eclipse. Only when the geometry of Sun, Earth, and Moon aligns near the points where the two orbital planes cross do eclipses occur. Most months, the Moon continues its cycle without such exact alignment. The orbit is therefore orderly but not rigidly simple. It combines repetition with gentle misalignment, enough to create variety without disorder. Another quiet feature of the orbit is that its orientation does not remain fixed forever. The line connecting perigee and apogee slowly turns, and the places where the lunar orbit crosses Earth's orbital plane also shift over time. These gradual rotations are part of the long-term geometry of the system. They do not throw the Moon into a new regime. Instead, they show that an orbit can be stable while still evolving in detail. The Moon's path is best understood not as a drawn ring around Earth, but as a motion governed by repeated patterns layered over other repeated patterns. The basic circuit remains secure, while the exact geometry slowly cycles through longer intervals. Within this enduring orbit, the Moon is also moving away from Earth, though very slowly. Modern measurements using laser pulses reflected from instruments placed on the lunar surface show that the average distance increases by about 3.8 centimeters each year. The change is far too small to notice in life. Across a single human lifetime, it amounts to only a few meters. Against the scale of the full Earth-Moon distance, the yearly increase is tiny, yet over immense spans of geological time, that tiny rate becomes significant. It reveals that the Moon's path is not only stable, it is also gradually expanding. This outward drift does not mean that the Moon is escaping from Earth or drifting off at random. It remains securely bound in orbit. The increase in distance is slow, measured, and consistent with the long history of the Earth-Moon system. Ancient evidence preserved in rocks and layered sediments indicates that the Moon was once closer to Earth than it is now, and that Earth's day was once shorter. The present orbit therefore belongs to a longer story of gradual change. But at this scale, the most important truth is simply geometric. The Moon's path around Earth is real, measurable, slightly oval, gently tilted and slowly widening. From Earth, all of this motion becomes visible as changing position and changing light. The moon advances eastward against the stars from night to night. It rises later each day by roughly 50 minutes on average, though the exact amount varies. Its face remains turned toward Earth because its rotation matches its orbital period, so one hemisphere stays mostly in view. Even here, the word mostly is important. Small oscillations called librations allow Earth to see a little more than 1/2 of the lunar surface over time. These subtle shifts do not break the overall rule of the orbit, they refine it. The moon remains a body in regular motion, close enough for its details to be known and distant enough for its path to be traced as a whole. The orbit, then, is neither static nor erratic. It is a calm structure made of repeating departures and returns, slight tilts, changing speeds, and a perceptible long retreat. The moon circles Earth in a path that holds together over ages, changing only by measured degrees. In the sky, this appears as serenity. In science, it appears as a system whose distances, periods, and orientations can be observed with extraordinary precision. The farther story of why that orbit changes belongs elsewhere. Here, in the space between Earth and Moon, the essential fact is the path itself broad, stable, slightly elliptical, and slowly opening with time. Between Earth and the Moon lies a wide interval of open space, but gravity crosses that interval without any visible beam or thread. It is the relation that keeps the Moon in orbit and keeps Earth and Moon bound to one another. Gravity here is not simply a general attraction between two distant masses, it has structure across distance. The pull that the Moon exerts is stronger on the side of Earth nearest to it, weaker at Earth's centre, and weaker still on the far side. That gradual change from one side of the planet to the other is the key to the tides. A tide, in its most basic physical meaning, is the effect of a changing gravitational pull across an extended body rather than the pull on a single point. If Earth were only a mathematical point, the Moon's gravity would pull on it in one simple way. But Earth has size. One side is closer to the Moon by thousands of kilometers, and the opposite side is farther away. Because gravity weakens with distance, the lunar pull cannot be identical everywhere across the planet. The near side feels a slightly stronger attraction toward the Moon. The middle of Earth feels a slightly weaker attraction. The far side feels the weakest attraction of all. These differences are small compared with Earth's own gravity, which is why the planet does not come apart under the Moon's influence. Yet small does not mean unimportant. Over planetary scales, even a slight difference matters when it acts continuously and repeats with regular motion. This unevenness is often called a gravitational gradient. The word gradient means a change from place to place. In this case, it describes how the Moon's pull varies across Earth's width. That variation is the tide-generating part of lunar gravity. The whole Earth is attracted toward the Moon, but not every part of Earth is attracted equally. Tidal effects therefore do not arise from gravity alone in the broadest sense. They arise from unequal gravity, from the fact that one part of a large body is pulled a little more strongly than another. This distinction is quiet but essential. It is the difference between simple attraction and stretching. Another subtlety enters at once. Earth and the Moon do not behave as a fixed planet with a separate object merely circling it. Both revolve around their common centre of mass. This shared motion means that every part of Earth participates in the monthly turning of the Earth-Moon pair. The centre of Earth follows one path around that common centre, and points on the surface are carried along with it. When that shared motion is compared with the changing strength of the Moon's pull across Earth, the full tide generating pattern appears, on the side of Earth nearest the Moon, lunar gravity exceeds the pull felt at the centre, so material there is drawn slightly more strongly moonward. On the far side, the Moon's gravity is weaker than the pull at the centre, so that side is left slightly behind relative to the centre's motion. In both directions, the result is a tendency toward differential stretching along the Earth-Moon line. This is why tidal theory produces two opposite zones of outward displacement rather than only one. One lies on the side facing the Moon, where the pull is strongest. The other lies on the opposite side, where the pull is weakest relative to Earth's centre. The geometry can seem counterintuitive at first because ordinary language tends to imagine tides only as matter being drawn toward the Moon. That is only half of the picture. The other half comes from comparing all points on Earth to the motion of the planet's centre. Tidal physics is therefore relational. It depends not only on how strongly the Moon pulls, but on how differently it pulls from one location to another, across the gap between Earth and Moon. This difference falls off rapidly with distance. If the Moon were moved much farther away, the tide-generating force would become much weaker, even if its total gravitational attraction remained important for orbital motion. If it were much closer, the gradient would become stronger, and the stretching effect across Earth would increase sharply. This sensitivity to distance explains why the Moon, despite being less massive than the Sun, is the dominant source of terrestrial tides. The Sun exerts a stronger overall gravitational pull on Earth because of its enormous mass, but it is so far away that the difference in its pull across Earth's diameter is smaller than the lunar difference. For tides, closeness matters profoundly. The important action in this region of space is therefore not a dramatic force, but a persistent imbalance. Every point on Earth is falling freely within the wider Earth-Moon system, yet each point is not falling in exactly the same way. The near side is urged a little more strongly toward the Moon. The far side is urged a little less strongly. Between those two limits lies a smooth transition. This is enough to deform the shape that a perfectly fluid Earth would take under lunar gravity. Real Earth is not perfectly fluid, and its actual response depends on ocean water, crust, mantle, atmosphere, rotation, and the arrangement of continents. Those details belong to the planet itself. Across the open space between the two worlds, the essential cause is simpler gravity changes from place to place. This changing pull also acts in the opposite direction. Earth raises tides on the Moon by the same physical principle, and because Earth is much more massive, its tide-generating effect on the Moon is strong. Over long spans of time, that mutual tidal interaction shapes the motion of both bodies. Even without following those consequences, the basic geometry is already complete. Two worlds face one another across space. Each exerts gravity on the other. Because each world has size, the pull is never perfectly uniform across its entire body. Non-uniform gravity creates stretching, and stretching is the root of tides. The gap between Earth and Moon is therefore not empty. It is a domain organized by distance, mass, and motion. Gravity weakens outward through that space according to exact rules, and those rules create a pattern of unequal attraction across Earth. What appears from the ground as a familiar connection between the Moon and earthly rhythms begins here. In this invisible gradient spanning hundreds of thousands of kilometers, the Moon does not need to touch Earth to shape it. It only needs mass, distance. And the difference between nearer and farther points across a world with real size. Earth does not receive the Moon's tide-generating pull as a rigid stone would receive a brief tap. It responds as a whole planet. Rock, water, and air each shift in their own way under the same changing gravitational pattern. The response is smeros the entire globe. The ocean surface rises and falls most visibly. The solid body of the planet also flexes. Even the atmosphere participates. A tide is therefore not only an event at the shore, it is a distributed planetary adjustment, a slow and repeated reshaping of Earth under the combined pull of the Moon and the Sun. The most familiar part of that reshaping is the ocean. Water can move more freely than rock, so the tidal response is easiest to notice there. In the simplest picture, the ocean tends toward two broad swellings aligned roughly with the Earth-Moon line, one on the side facing the Moon, and one on the far side. As Earth turns, coastlines move through this changing pattern, and sea level at any one place appears to rise and fall. This simple picture is useful, but the real ocean is more complicated. Earth is not covered by one smooth, uniform shell of water. Continents interrupt the flow. Ocean basins differ in width and depth. Narrow seas, wide shelves, and submarine ridges alter how water moves. For that reason, actual tides in the ocean are not identical from place to place, and they do not form a perfect pair of bulges circling a featureless planet. Even so, the underlying cause remains planetary. The whole ocean system responds to tidal forcing, not only the water at the edge of a beach. Beneath the ocean, the solid Earth also deforms. This is called the body tide or the solid Earth tide. The phrase means that the crust and deeper layers yield slightly under tidal forces rather than remaining perfectly fixed. Earth is strong, but it is not perfectly rigid. Its rocks can bend by very small amounts when a force acts on the entire globe. Sensitive instruments detect this motion clearly. The ground beneath a quiet observatory, a plain, or a mountain, does not stay absolutely still during the lunar cycle. It rises and falls by small amounts as the planet flexes. The scale is modest, commonly on the order of a few tens of centimeters, but the existence of that motion is important. It shows that tides belong to the whole Earth, not only to the sea. This flexing happens because rock, given enough scale and enough time, behaves with a degree of elasticity. Elasticity is the tendency of a material to change shape under force and then recover when the force changes. In everyday life, rock seems completely stiff. On planetary scales, under weak but persistent forcing, it yields slightly. The Moon's gravity therefore draws not only on the ocean's surface but on the body of the planet itself. The solid Earth develops tiny tidal distortions that follow the changing geometry of the Earth-Moon system. These distortions are far too small to notice in ordinary life, yet they matter in geodesy, the science of measuring Earth's shape, size, and changing surface with great precision. Above the land and sea, the atmosphere also experiences tides. Air has mass, and the changing gravitational pull acts on it as well. In addition, the atmosphere responds strongly to daily heating by sunlight, so atmospheric tides arise from more than one cause. The gravitational part linked to the Moon is smaller and less obvious than ocean tides, but it is present in subtle pressure patterns and motions of the air. This makes the full terrestrial tide a three-part response. Ocean water shifts visibly, solid ground flexes measurably, the atmosphere adjusts more delicately. Together they show that tidal forcing is not confined to any single layer of the planet. Because all three parts of Earth respond at once, the real tide is not a simple lifting of water toward the Moon. The ocean moves across a surface that is itself flexing. Coastlines rise and fall with the ground beneath them. The atmosphere presses on the sea surface while also changing in density and motion. Every measured tide at a particular location is therefore the local expression of a global process. What appears in a harbour gauge or along a tidal flat is only one visible part of a larger adjustment involving the entire planet. What appears in a harbour gauge is local. The cause remains planetary. Rotation adds another level of complexity without changing the basic idea. Earth turns once each day while the main tidal forcing pattern shifts with the moon's motion around the planet. Because of that turning, no fixed place on Earth remains permanently under one tidal swelling. Instead, places move through the evolving pattern. In a simplified world with a uniform deep ocean, that movement would produce a more regular rise and fall. On the real Earth, the turning planet, broken ocean basins, and uneven coastlines create regional differences in timing and height. Some coasts have 2 high tides and 2 low tides in a lunar day. Some have strong inequality between successive tides. Some have a dominant single daily cycle. These differences do not mean the tide has separate causes in separate places. They mean one planet-wide forcing pattern is expressed through different local shapes and depths. The Sun also contributes to the total tidal response of Earth. Its tide-generating effect is weaker than the Moon's, but it acts continuously and can reinforce or partially offset the lunar effect depending on the alignment of the system. When Sun, Earth, and Moon lie more nearly along one line, the combined tide is larger. When the geometry forms a broad angle, the combined tide is smaller. This too is felt not only by the sea but by the body of Earth and the atmosphere. The entire planet participates in these repeated adjustments. Seen in this way, Earth under tidal forcing is never perfectly still. Its surface waters redistribute. Its rocky body flexes and relaxes. Its air shifts in response to gravity and heat. None of these changes is violent on the planetary scale. They are rhythmic, limited, and continuous. The Moon does not merely raise water at the shore. It helps impose a faint but measurable pulse on the whole planet. Earth answers not as separate pieces, but as one connected world with different materials responding according to their nature under the same celestial pull. The Moon's slow departure from Earth is not a poetic idea drawn from the changing sky. It is a measured physical fact. The rate is small, almost too small to imagine in everyday terms, yet modern instruments detect it directly. The most precise method begins with light. During the Apollo missions, astronauts placed special mirrors on the lunar surface. Robotic landers from the Soviet lunar program also contributed reflective devices. These instruments are called retroreflectors. They are designed so that a pulse of light sent toward them returns in the direction from which it came. From Earth, observatories fire short laser pulses toward the Moon, wait for the reflected light to return, and measure the travel time with extraordinary precision. Because light moves at a known speed, the round-trip time reveals the distance between Earth and the reflector with remarkable accuracy. This work is known as lunar laser ranging. It turns the Earth-Moon distance into a quantity that can be monitored again and again, year after year, with the same underlying method. No human eye can notice the Moon edging away. No ancient observer could have seen the orbit widening directly from one generation to the next. The change is too small for that. But a laser pulse does not rely on appearance. It relies on timing, geometry, and repetition. Over many decades of observations, the pattern becomes clear. The average distance to the Moon increases by about 3.8 centimeters each year. This is not an estimate based only on theory. It is an observed trend emerging from a long record of measurements. The achievement rests on patience as much as technology. A beam of light must travel across hundreds of thousands of kilometers, strike a device only modest in size, and return through Earth's atmosphere to a receiver capable of detecting a tiny signal. Most of the light sent outward does not return to the instrument. The task is delicate. Weather matters. Atmospheric conditions matter. The exact positions of Earth and Moon matter. The rotation of Earth, the motion of tectonic plates, and the subtle orientation of the Moon all enter the calculation. Yet those complications do not weaken the conclusion. They are precisely the kinds of factors that a mature measuring science learns to correct for. Over time, the data converge on a stable result. The Moon is receding. These laser measurements do more than reveal a single number. They show that the Earth-Moon system is a dynamic system that can be tracked with exquisite precision. The same observations test aspects of orbital motion, the Moon's physical libration, and even parts of gravitational theory. But for the history of the Earth-Moon distance, the most important outcome is simple. Modern science watches the widening directly. It does not have to infer the present-day trend from distant consequences alone. The system is active now, and the instruments are sensitive enough to see it. Still, the modern record covers only a very short span compared with the age of Earth and the Moon. Decades are powerful for precision, but tiny compared with billions of years. To know whether the Moon has truly been moving outward over deep time, science turns to natural archives preserved in rock. These archives do not contain a written statement about lunar recession. They preserve rhythms, counts, and repeated patterns that can be interpreted through physics and geology together. The most important among them are tidal rhythmites, finely layered sediments laid down in settings influenced by repeated tidal currents. A rhythmite is a sequence of layers that forms through regular environmental pulses. In tidal settings, currents strengthen and weaken with changing water levels, carrying and dropping sediment in patterns that can be repeated over days, months, and longer cycles. Under the right conditions, those patterns remain preserved after burial and lithification. The process by which loose sediment becomes rock. When geologists find ancient tidal deposits with clear layering, they can sometimes count recurring bundles and compare them with known tidal and seasonal cycles. From this, they estimate how many days fit into a month in the distant past, or how many days fit into a year. Since the length of the year in orbital terms remains set by Earth's path around the Sun, a greater number of days in a year means each day is shorter than it is now. Shorter days imply that Earth spins faster in the past. When that evidence is combined with the physics of the Earth-Moon system, it supports the conclusion that the Moon was closer to Earth long ago. Some of the strongest examples come from ancient sedimentary formations in which tidal layering is unusually clear. These records are not always easy to read. Later deformation, erosion, chemical alteration, and incomplete preservation can blur the original signal. Geologists therefore treat them carefully. Different outcrops vary in quality, and interpretations are tested against independent lines of evidence. Even with those cautions, the overall picture remains consistent. Ancient Earth often shows more days in a year than the present 365. That means faster rotation, in turn, fits a younger Earth-Moon system in which the Moon orbits at a smaller distance. Other natural records support the same broad conclusion. Growth patterns in some fossil organisms, especially certain ancient corals and shelled marine animals, preserve daily and seasonal increments. Much like tree rings record repeated growth, these organisms can preserve fine bands linked to day-night and annual cycles when well preserved. They offer another way to estimate the number of days in a year at the time the organism lived. These records also tend to indicate that the distant past contains shorter days than the present. The details differ from one fossil group, and one geologic age to another, and the method carries uncertainties of preservation and interpretation. Yet taken together with sedimentary tidal records, they reinforce the same direction of change. What matters most is convergence. Laser ranging measures the moon receding now. Geological and fossil records indicate that Earth rotates faster in the past, and therefore that the Earth-Moon system was configured differently. Celestial mechanics provides the framework connecting these observations. Each line of evidence has its own strengths and limitations. The laser method is extremely precise but covers only recent decades. Ancient rocks reach far back in time but require interpretation and careful screening. Fossil growth patterns add another archive, also valuable but not perfect. None of these records stands alone in isolation. Together they produce a coherent history. The moon's departure is therefore visible in two ways. It is visible directly in the present by timed pulses of light. It is visible indirectly in the deep past by rhythms locked into stone and skeleton. One method watches the distance itself, the other recovers the changing tempo of Earth's rotation and tidal cycles. Both lead to the same conclusion. The moon is farther away now than it once is, and the widening of the orbit belongs not only to theory, but to measurement across the shortest modern record and the longest geological memory. In the earliest history of the solar system, Earth is not yet the settled world it later becomes. It is still growing through repeated collisions with smaller bodies, still hot from accretion, and still taking shape as dense material sinks inward and lighter, silicate rock remains above. In that young environment, the moon is not yet present. The pair that now seems so familiar does not begin as two finished bodies quietly arranged in space. It begins in violence, heat, and rearrangement. According to the leading scientific explanation, a large protoplanet, often described as roughly Mars-sized, strikes the young Earth after much of Earth has already formed. The impact is enormous. It does not simply gouge a crater, it disrupts the outer rocky layers of the colliding bodies and sends great quantities of material outward. This picture is called the giant impact hypothesis. It becomes the leading explanation because it fits many of the main properties of the Earth-Moon system better than older ideas do. Earlier suggestions propose that the Moon forms elsewhere and is later captured by Earth, or that Earth and Moon form side by side from the same local cloud of material, or that the Moon splits away from a rapidly spinning young Earth. These ideas each explain part of the problem, but they struggle with the whole set of observations. The capture idea has difficulty accounting for the present orbit without an efficient way to remove energy. The simple co-formation idea does not easily explain the detailed chemical relationship between Earth and Moon. The fission idea does not fit modern understanding of Earth's rotation and internal history. The giant impact model, though still refined in many versions, remains the framework that best matches the evidence. Much of that evidence comes from the Moon itself. Samples returned by the Apollo missions transform understanding of lunar origin. They show that lunar rocks are very old, and that the Moon forms early in solar system history. They also show that the Moon is strongly depleted in substances that vaporize easily when heated, which suggests a high-energy event. At the same time, the chemical and isotopic character of lunar rocks is strikingly similar to that of Earth's outer rocky layers. Isotopes are atoms of the same element with different masses, and their relative abundance acts like a signature of origin. The closeness of these signatures in Earth and Moon materials points to a deep connection between the two bodies. It indicates that the Moon is not simply a stranger captured from another region. It forms out of material intimately linked to Earth. In the giant impact picture, that relationship arises naturally. A large impactor collides with the young Earth in an oblique blow. The collision heats, melts, and partly vaporizes rocky material from Earth's outer layers and from the impactor itself. Some of this material escapes entirely, but a significant portion enters orbit around Earth as a hot disk or cloud of debris. Within that orbiting material, collisions continue. Fragments strike, merge, and exchange momentum. Over time, or perhaps in some models very quickly, the debris gathers into a single dominant body. That body becomes the Moon. Earth remains the larger survivor, though profoundly changed by the event. The exact details remain uncertain. Scientists continue to test different versions of the impact's slower or faster collisions, different impact angles, different masses for the impactor, different amounts of mixing between Earth material and impactor material, and different pathways by which orbiting debris becomes a moon. Some simulations produce a disk that later accretes into the Moon over months or years. Some more recent simulations suggest that a moon-like body could form much more rapidly, perhaps even within hours under certain conditions. What is broadly agreed upon is the central event itself. A giant collision in the early solar system creates the material from which the Moon forms. What remains under active study is the precise geometry, timing, and proportion of source material. The newly formed Moon is not the cool, cratered, quiet object seen today. Evidence indicates that it begins in a molten state. Much of its outer part is a global magma ocean, a deep layer of melted silicate rock. In this hot early Moon, minerals separate as the molten material cools. Denser minerals sink, while lighter minerals rich in calcium and aluminum float upward and help create the first crust. This helps explain the widespread anorthosite of the lunar highlands, rock that is consistent with flotation from a magma ocean. The Moon's early surface is therefore not stable ancient ground from the start. It is the top of a cooling molten world. Earth after the impact is also profoundly altered. The collision likely leaves the young planet with a renewed ocean of magma, or at least widespread melting near the surface. The atmosphere, if one can yet use that word in its later sense, is not a calm blanket of nitrogen and oxygen. It is a hot environment shaped by vaporized rock and volatile compounds released by intense heating. The Earth-Moon system at this stage is not familiar in appearance, but the physical pairing has begun. Two bodies now exist where before there is one growing proto-Earth and a separate impactor. Their shared history starts in common debris and common heat. The young Moon also begins much closer to Earth than it is now. It does not form at the present distance. The early sky above Earth, if it could be seen through the hot aftermath, would hold a much larger Moon. Its gravitational influence would be stronger at that smaller distance, and the pair would be more tightly coupled than in the modern arrangement. This is one reason the origin story matters so much. It is not only about where the Moon comes from, it is about how the Earth-Moon system begins in a very different state from the one observed today. Even within the giant impact framework, the Moon's exact composition continues to challenge researchers. The close isotopic similarity between Earth and Moon is especially important. It suggests either that much of the Moon forms from Earth-derived material, or that the impactor and Earth form from very similar reservoirs in the inner solar system, or that extensive mixing occurs during or after the impact. Different models emphasize different combinations of these possibilities. None of this uncertainty weakens the larger conclusion. It refines it. The origin of the Moon is not a solved problem in every detail, but the broad narrative is strongly constrained by observation. So the birth of the Earth-Moon pair is not a gentle separation. It is a planetary collision followed by reassembly. It turns two early bodies into one altered Earth and one newly formed Moon. bound thereafter in orbit. From that event come the Moon's small metallic core, its early molten state, its depleted volatile content, and its deep chemical kinship with Earth's rocky exterior. In the silent record of lunar rocks, in orbital dynamics, and in modern numerical models, the same picture returns again and again. The Moon begins as consequence, not accident, the enduring offspring of a collision in the young solar system. The outward motion of the Moon is not a drift without cause. It is part of a slow exchange built into the Earth-Moon system itself. The key idea is angular momentum, a term for motion carried in rotation and orbit. A spinning planet has angular momentum because it turns around its axis. An orbiting moon has angular momentum because it moves around its planet. In the Earth-Moon pair, these two forms are linked through gravity and tides. Over long spans of time, some of the motion bound up in Earth's spin is transferred into the Moon's orbit. That transfer does not happen by contact. It happens through the repeated deformation of Earth under lunar gravity, and the fact that Earth rotates more quickly than the Moon goes around it. Earth turns once in about 24 hours, while the Moon takes much longer to complete one orbit around Earth. Because Earth rotates faster than the Moon moves around the planet, the tidal distortions raised by the Moon are not held exactly on the Earth-Moon line. The planet's rotation carries them slightly ahead. In a world with no internal friction, matter would adjust perfectly and without delay to the Moon's pull. Real Earth does not behave that way. Water sloshes through ocean basins, rubs against the seafloor and the edges of continents, and meets resistance from turbulence and changing depth. The solid Earth also flexes imperfectly and loses a small amount of energy as heat. Because of these delays and frictions, the tidal bulges are displaced a little in the direction Earth is turning. That small offset matters. Once the bulges lie slightly ahead of the line pointing directly at the Moon, their gravity pulls on the Moon from a shifted direction. The pull is no longer aimed only inward toward Earth. It has a forward component as well. This forward gravitational tug gives the Moon a little extra orbital momentum. In effect, Earth's rotating tidal bulges try to drag the Moon ahead in its path. The Moon responds not by spiraling inward, but by moving to a higher orbit. In orbital mechanics, a body that gains angular momentum in this way can end up farther from the central body, while its orbital motion adjusts to the new distance. The Moon therefore recedes because it is being fed orbital angular momentum by the rotating Earth. At the same time, Earth pays the price for that transfer. When Earth's tidal bulges pull forward on the Moon pulls back on those bulges. This backward pull exerts a torque on Earth. A torque is a twisting influence that changes rotation. In this case, it acts against Earth's spin. The result is a very gradual slowing of the planet's rotation. Earth is not braking because it rubs against empty space. It is braking because its own tidal distortion, carried slightly ahead by rotation, allows the Moon's gravity to act as a long lever against the spin. The system is therefore reciprocal. Earth pushes the Moon outward through the gravity of the offset bulges, and the Moon slows Earth by pulling back on the same displaced mass. The exchange involves energy as well as angular momentum, but the two do not change in identical ways. Earth's rotation contains a large store of energy. As tidal friction operates, some of that rotational energy is lost from organized motion and becomes heat, mainly in the oceans and to a lesser extent in the solid Earth. Another part of the changing energy budget appears in the Moon's orbit. A more distant orbit has greater orbital energy in the sense used in celestial mechanics, even though the Moon moves more slowly at that greater distance. This is one of the quiet subtleties of orbital motion. To move the Moon farther away, The system must transfer angular momentum to the orbit and alter the balance of energy at the same time. Earth's spin slows, the Moon's orbit expands, and some of the original rotational energy is dissipated as heat. The process is orderly, not waste-free. This means the present recession of the Moon is not separate from tides. It is tides extended through time. Every tidal cycle carries a minute part of the same exchange. On short timescales, the changes are almost invisible. Ocean water rises and falls, the ground flexes, energy is dissipated, the geometry resets and repeats. On long time scales, those tiny repeated imbalances accumulate into measurable change. Earth rotates more slowly than it once does, and the Moon orbits farther away than it once does. The mechanism linking those two facts is the gravitational and frictional coupling of the system. The process also helps explain why the Moon is already tidally locked while Earth is not. The Moon, being smaller, responds more strongly to Earth's tide-generating effect relative to its size, and over time its rotation slows until one side remains turned toward Earth. That state is stable and already achieved. Earth, being much larger and possessing far more rotational angular momentum, changes more slowly. It continues to spin much faster than the Moon orbits, so the tidal bulges continue to lead and the transfer continues. The modern Earth-Moon system therefore sits in an intermediate stage of a long evolution, still exchanging motion through tides because the two bodies have not reached mutual synchrony. The strength of this transfer is not constant across all ages. It depends on the arrangement of oceans, the shapes of continents, the depth of seas, and the detailed response of Earth's interior. Tidal dissipation can be stronger in some configurations than in others. For that reason, the present rate of lunar recession cannot simply be extended backward unchanged through the whole age of the system. The broad mechanism remains the same, but its efficiency varies. This is an important scientific caution. The Earth-Moon exchange is well established. Yet the exact pace of that exchange through deep time depends on the changing structure of the planet. What remains fixed is the direction of the transfer from Earth's faster spin into the Moon's widening orbit. Seen in full, the process is elegant. The Moon raises tides on Earth. Earth's rotation carries those tides slightly ahead. The displaced mass pulls the Moon forward. The Moon moves outward. The Moon's gravity pulls back on the bulges. Earth's spin slows. Friction turns part of the organized motion into heat. Through this continual action, the Earth-Moon system redistributes angular momentum while preserving the deeper physical order of the pair. The Moon does not leave Earth because the bond weakens. It moves away because the bond, acting through tides, steadily transfers motion from one form to another. As the Moon moves outward, Earth changes inwardly in a quieter but equally important way. The planet spins more slowly. This change is extremely gradual, far too small to feel from one lifetime to the next, yet it is built into the same tidal exchange that carries the Moon away. Earth begins its history rotating faster than it does now. Over immense spans of time, tidal friction acts against that spin. The result is a steady lengthening of the day. A day on Earth is not fixed for all ages. It is a changing interval, shaped by the transfer of angular momentum from Earth's rotation into the Moon's orbit, and by the small but continuous loss of rotational energy as heat. In the present world, one full rotation relative to the Sun defines the familiar day-night cycle. This interval feels fundamental because every routine and every clock is built around it. Yet the modern 24-hour day is only a temporary value within a much longer history. In the distant past, Earth turns more quickly, so sunrise and sunset follow one another sooner. This same year therefore contains more individual days, not because Earth takes longer to go around the Sun, but because each spin is shorter. The year is set mainly by Earth's orbit around the Sun. The day is set by Earth's rotation on its axis. When the spin slows while the orbit remains nearly the same, the number of days in a year decreases. The mechanism is the one already at work in modern tides. Because Earth rotates faster than the Moon orbits, tidal bulges are carried slightly ahead of the Earth-Moon line. The Moon pulls back on those displaced bulges and exerts a braking torque on the planet. That braking does not stop the rotation, it merely reduces it by a minute amount over long intervals. The modern slowing is very small, measured in milliseconds per century on average, though the exact rate varies and short-term effects from the atmosphere, oceans, and the shifting distribution of mass within Earth complicate the immediate record. These complications do not change the long trend. Over geological time, the rotation slows. This slow change has been measured not only in modern astronomical observations, but also in ancient natural archives. Some of the most persuasive records come from tidal rhythmites, layered sediments formed in environments where water movement follows repeated tidal cycles. When conditions are favourable, these layers preserve nested patterns that reflect daily, monthly, and seasonal rhythms. By counting the smaller laminae within larger recurring bundles, geologists estimate how many tidal cycles occur within a month, or how many daily cycles occur within a year at the time the sediment is laid down. These records indicate that ancient Earth contains more days in a year than the present Earth does. That means each day is shorter. Fossil growth patterns tell a similar story. Some ancient corals, shelled organisms, and other marine life forms lay down fine growth bands linked to daily light cycles and broader annual changes. When such fossils are exceptionally well preserved, researchers can count these increments and compare the number of daily bands within yearly growth patterns. The numbers often exceed the modern count of days per year. In rocks hundreds of millions of years old, a year may contain around 400 days or somewhat more, depending on age and interpretation. That does not mean the year itself is longer. It means Earth spins faster, fitting more shorter days into the same orbital period around the Sun. The oldest sedimentary records that preserve tidal signals point to an even more rapidly rotating Earth in the deep past. In some very old formations, the evidence suggests days significantly shorter than modern days. The exact values remain subject to uncertainty because ancient rocks can be altered, compressed, partly eroded, or incompletely exposed. Researchers therefore interpret them with caution, testing different depositional models and comparing one site with another. Even with these limitations, the broad pattern is stable. The farther back one goes, the shorter the day tends to be. Earth's rotation is slowing across deep time. This slowing affects the planet's history in ways that are subtle on human scales, but profound on geological ones. A faster spinning Earth has a different tempo of heating and cooling between day and night. Winds, ocean circulation, and atmospheric waves respond to the rate of planetary rotation. Even without following those consequences outward, the basic physical truth remains simple. Rotation is not merely a background property. It is an evolving part of Earth's state. The planet inherits a much faster spin from its early formation and gradually surrenders some of that motion through tidal interaction with the Moon. The record of this slowing is not perfectly smooth. Earth's rotation on short timescales can speed up or slow down slightly because mass moves within the atmosphere, the oceans, the core, the mantle, and the ice sheets. Large earthquakes redistribute mass. Seasonal winds alter angular momentum exchange between air and solid Earth. Melting ice changes the spread of water over the surface. For this reason, the exact length of day fluctuates around the long-term trend. These variations are real and measurable, but they are temporary ripples on top of a much larger pattern. Over millions and billions of years, tidal breaking dominates the direction of change. There is also a deep importance to the lengthening of the day. It ties immediate experience to celestial mechanics. The alternation of light and darkness seems local to life on the surface. In fact, it is linked to a planetary process spanning hundreds of thousands of kilometers. The Moon, by raising tides on Earth, participates in shaping the duration of every day. The daily rhythm familiar to the present age therefore carries the imprint of a long relationship between planet and moon. Seen across the full history of the system, the modern day is a middle stage. It is longer than the short days of ancient Earth, and shorter than the days Earth will have in the future if the same broad tidal evolution continues. The pace is so slow that no generation notices it directly in ordinary life. Only precise measurements and preserved geological rhythms make it visible. Yet once those records are assembled, they reveal a planet whose spin is changing patiently and continuously. Earth turns, but not always at the same rate. Its day lengthens because the Moon is engaged in a long mechanical exchange that steadily redraws the tempo of the planet's rotation. The Moon's influence becomes most visible in the ocean. Water can flow, spread, and adjust more readily than rock. So the tidal response that gravity begins across the whole Earth reveals itself most clearly at sea. Yet the ocean does not behave like a loose skin sliding freely over a perfect sphere. It is deep in some places and shallow in others. It is divided by continents, narrowed by straits, widened into broad basins, and shaped by the seafloor beneath it. For that reason, the lunar tide in the ocean is both global and local at once. Its cause is shared across the planet, but its expression depends on the structure of each basin through which the water moves. In the simplest physical picture, the ocean tends toward two broad regions of higher sea level and two broad regions of lower sea level during the main tidal cycle. One higher region lies roughly on the side of Earth facing the Moon, and another lies on the opposite side. As Earth rotates beneath this pattern, and as the Moon continues its orbit, different parts of the ocean pass through these changing elevations. If Earth were fully covered by an ocean of uniform depth and no continents interrupted the flow, the resulting tide would follow a comparatively simple rhythm. Real oceans are more complicated, yet that ideal image remains useful because it captures the underlying forcing. This redistribution is not instantaneous. Ocean water has inertia, the tendency of moving matter to keep moving. When the tide-generating forces shift, the ocean does not leap at once into perfect equilibrium. It responds with delay and travelling motion. Waves of tidal energy move through the ocean basins, reflecting from coasts, bending around land masses, and interacting with one another. The daily turning of Earth also affects their motion through the Coriolis effect, the apparent deflection that arises in a rotating frame. This gives real ocean tides their complex geography. The sea does not simply rise under the Moon and sink elsewhere. It oscillates as a dynamic fluid on a rotating planet. For this reason, tides across the open ocean are often smaller in height than people expect, commonly measuring tens of centimeters to around a meter in many regions, even while the total mass of moving water is immense. What makes the ocean tide powerful is not only the vertical difference in level, but the vast horizontal transport involved. As the surface adjusts, large bodies of water move across enormous distances. In some places, the timing of this motion aligns with the natural oscillation period of a basin, and the tide becomes amplified. In other places, Interference between different tidal components reduces the visible range. The moon's forcing therefore meets an ocean that has its own geometry and preferred modes of motion. Among the most important lunar rhythms is the semidiurnal cycle, a pattern in which many locations experience 2 high waters and 2 low waters during a lunar day. A lunar day is the interval required for a place on Earth to rotate back beneath the moon, which is slightly longer than a solar day because the moon advances in its orbit while Earth turns. In other regions, the daily pattern becomes mixed, with 2 unequal highs and lows, or predominantly diurnal, with 1 stronger rise and 1 stronger fall each day. These differences reflect the interaction between the global tide-generating forces and the shapes of real ocean basins. They mean the ocean translates one celestial rhythm into several regional forms. The sun adds its own tidal forcing, weaker than the moon's but still important. When sun, Earth, and moon lie more nearly in a line at new moon or full moon, their effects reinforce one another and produce spring tides, the larger combined tides. The word spring here refers to a leap or rise, not to a season. When the sun and moon stand at a broader angle as seen from Earth, around the first and third quarter phases, their effects partly oppose one another and produce neap tides, the smaller combined tides. This fortnightly change gives the ocean another layer of rhythm. The strength of the daily tidal cycle waxes and wanes over the course of the lunar month. Longer cycles appear as well. Because the moon's orbit is elliptical, tides tend to be somewhat stronger when the moon is nearer Earth and weaker when it is farther away. Because the lunar orbit is tilted and its orientation slowly shifts, the moon's changing declination alters how tidal energy is distributed between hemispheres and between daily patterns. These refinements matter because they show that the tide is not one single pulse repeated without variation. It is a family of closely related cycles, each traceable to orbital geometry. The ocean records these cycles continuously in motion, level, and current, across the major ocean basins. Tidal motion often organizes itself around amphidromic systems, broad rotating patterns in which the tidal wave circulates around points of minimal range. Near such points, the rise and fall of sea level can be very small, while farther away the range grows larger. These patterns emerge from the interaction of basin shape, Earth's rotation, and wave propagation. They are a reminder that the ocean is not passively lifted and lowered as a single sheet. It supports moving tidal waves whose phase, height, and direction vary across space. Even with this complexity, the result at sea is one of strong regularity. Mariners and ocean scientists can predict tides successfully because the governing motions are astronomical and therefore highly ordered. Once the form of the response in a given basin is known, the future pattern can be calculated with impressive precision. Storms can temporarily raise or lower local sea level. Winds can pile water against a coast or draw it away. Pressure systems can distort the surface. Yet beneath these changing weather effects, the lunar tide continues with patient regularity. It is a background pulse of the ocean itself. This regular rise and fall shapes marine physical conditions long before any living system responds to it. It determines when and how water masses accelerate, pause, reverse, and exchange position. It changes depth and pressure in repeating intervals. It sets a clock within the sea that is not made by human timekeeping and not governed by the sun alone. The ocean lives under many influences, including wind, heat, salinity, and Earth's rotation, but the moon gives it its clearest recurring motions. In the broad basins and across the open water, the lunar rhythm turns gravity into movement and movement into a lasting marine pulse. Where the open ocean meets the land, the lunar tide becomes a moving force that reshapes water, shore, and suspended material again and again. In these coastal regions, the rise and fall of sea level is only the most visible part of the process. Beneath that change in height, water from marshes and reverses direction with steady repetition. The shore is therefore not a fixed edge between sea and land. It is a zone of continual exchange, and the moon's tidal pull helps govern that exchange every day. Along an exposed coast, incoming tide lifts the water surface and allows waves and currents to reach farther inland across beaches, mudflats, rocky inlets, and estuarine margins. As the tide ebbs, water drains seaward through the same terrain, often by different pathways and at different speeds. This repeated flooding and draining creates strong horizontal movement. In narrow inlets and between islands, the currents can become swift because a large volume of water must pass through a small opening. In broad, shallow areas, the water may spread more slowly but across a wider surface. The exact form depends on coastal shape, seabed slope, bottom roughness, and the range of the local tide. Yet the essential pattern remains the same. Tidal motion does not simply raise the sea, it moves the sea laterally through the landscape. This motion stirs the coastal ocean. Mixing occurs when water masses of different properties are brought together and blended by turbulence and current shear. Shear means that adjacent layers of water move at different speeds or in different directions. Under a growing tide, faster water may pass over slower water or around obstacles, generating swirls and eddies. Under an ebbing tide, channels and estuary mouths may focus the returning flow and create new turbulence. Wind can add its own stirring, but tidal currents alone are often enough to keep nearshore waters in motion. In many places, this repeated agitation prevents the water from remaining neatly layered for long. One of the most important results is the redistribution of heat, salt, oxygen, and suspended matter. Fresh water from rivers tends to enter estuaries at the surface because it is less dense than seawater. Saltier water tends to penetrate landward at depth, where the geometry allows it. Tides work constantly on this arrangement. In some estuaries they mix the layers strongly, producing a more uniform water column from top to bottom. In others they create only partial mixing, so fresh and salt water remain somewhat distinct but exchange material across their boundary. In either case, the lunar rhythm drives circulation that would not occur in the same way without repeated tidal reversal. The estuary becomes a place where ocean water enters, river water departs, and both are modified by turbulence between them. Nutrients are carried within this movement. Dissolved compounds from rivers, wetlands, seafloor sediments, and the coastal ocean are transported back and forth by the tidal flow. Some are lifted from bottom waters or sediments into the sunlit upper layer, where they become available again for biological use. Some are swept seaward and diluted. Some are trapped for a time within channels, marsh creeks, or embayments, then released on a later cycle. Oxygen is circulated as well. Tidal currents renew shallow waters and help prevent stagnation in many coastal settings by replacing water that has lost oxygen with water from elsewhere. The degree of renewal differs from place to place, but the physical principle is broad and clear. Repeated water movement promotes exchange. Sediment responds in much the same way. Fine mud, silt, sand, and organic particles settle when water is calm and are lifted again when currents strengthen. Each tidal cycle therefore acts as a sorting event. Coarser grains may remain in high-energy channels and on exposed shores, while finer material accumulates where currents weaken, such as sheltered flats, marsh margins, tidal creeks, and inner estuaries. Over long spans of time, This repeated transport helps build landforms. Tidal flats expand and contract. Channels migrate. Sandbanks shift. Marsh platforms accrete through the deposition of fine sediment during flooding. Coastal landscapes are therefore not only shaped by storms or rivers, they are also shaped quietly by the daily work of the tide. The strength of tidal mixing often changes through the lunar month. Around spring tides, when the moon and sun reinforce one another, currents can become stronger and the stirred zone can deepen. Around neap tides, weaker forcing allows stratification, the layering of water by density, to rebuild more easily in some places. A coastal basin may therefore alternate between more mixed and more layered states on a roughly fortnightly rhythm. This is especially important in shallow seas and estuaries, where small changes in current strength can alter how far the water column mixes from surface to bottom. The coast does not experience one constant condition. It oscillates between stronger and weaker blending under the changing geometry of the Sun-Earth-Moon system. This physical pulse also controls how long water remains within a coastal embayment or estuary before being exchanged with the open sea. Some systems flush relatively quickly because tidal currents are strong and the basin is open. Others retain water longer because they are sheltered, stratified, or topographically complex. The term residence time describes this average stay. Tides do not determine residence time alone, since river inflow, wind, and basin shape also matter, but they are often central. By reversing flow and stirring boundaries, tides regulate how effectively coastal waters are renewed and how strongly local conditions accumulate. At the shoreline itself, this means that the margin between wet and dry is never merely a line. It is a band that migrates with the sea, sometimes over meters, sometimes over kilometers in very shallow terrain. Pools fill and drain. Sand is reworked. Mud cracks and softens in alternating exposure. Salt marsh creeks breathe in and out with each cycle. Mangrove margins, tidal flats, and rocky benches all experience the same celestial forcing translated into different local forms. The moon's pull reaches these places not as an abstract gravitational gradient, but as water in motion. The coast is therefore one of the clearest places where the moon's influence becomes material. It stirs, mixes, sorts, and exchanges. It links river water with seawater, bottom sediment with the upper layer, sheltered basins with the continental shelf, and the landward edge of the tide with the open sea beyond. Through these repeated currents, the moon helps maintain the restless physical texture of coastal waters. The rhythm is regular, but its effects are never entirely static. Every return of the tide renews the movement by which shores are shaped, and near-shore waters remain in circulation. Earth does not spin with its axis standing straight up relative to its path around the sun. Its axis is tilted. That tilt, called axial tilt or obliquity, is the angle between Earth's spin axis and the perpendicular to its orbital plane. At present it is little more than 23 degrees. This means the planet rotates with a persistent lean. The axis points in nearly the same direction in space over the course of a year while Earth moves around the Sun, so different parts of the globe receive changing angles of sunlight during the orbital cycle. The tilt is therefore a basic part of Earth's geometry. It is not a temporary accident in the sky, but a long-lived property of the planet's motion. Yet the axis is not absolutely fixed. A spinning body under external gravitational influence can change the direction of its axis through time. Earth behaves in this way because it is not a perfect sphere. Rotation makes the planet bulge slightly at the equator and flatten slightly at the poles. That extra mass around the equator gives the sun and the moon something to pull on. Their gravity exerts torques on the equatorial bulge, and those torques make the axis slowly change direction. the motion is known as precession. Precession is a gradual conical sweep of the spin axis, similar in principle to the slow change of orientation seen in a spinning top. Though the Earth-Sun-Moon system is much more regular and far more stable than any toy, because of precession, the direction in space toward which Earth's axis points is not permanent. Over many thousands of years it traces a slow circle. This change does not greatly alter the size of the tilt by itself. It mostly changes the orientation of the axis. Even so, the planet's rotational state is not inert. It is open to gravitational influence. The Moon is crucial here because it contributes strongly to the torque acting on Earth's equatorial bulge. Although the Sun is vastly more massive, the Moon is close enough that its effect on Earth's spin axis dynamics is large. Together, Sun and Moon drive the precession of Earth's axis, but the Moon provides a major share of that forcing. That contribution matters because the pace of precession helps determine how Earth's tilt responds to other long-term gravitational influences in the solar system. The planets perturb one another's orbits. Their gravitational interactions slowly alter orbital planes and other elements of motion through time. Earth is part of that larger system, so its orbital environment is not perfectly unchanging. If the rate at which Earth's spin axis precesses were very different, the planet could fall more readily into resonances with these other periodic influences. A resonance is a condition in which repeated forcing lines up efficiently with a natural or characteristic frequency of a system. When that happens, changes can grow larger than they otherwise would. In the case of planetary obliquity, resonances can allow the tilt to vary much more widely. The Moon helps keep Earth away from the most disruptive of those possibilities. By strengthening the torque on Earth's equatorial bulge, it increases the precession rate of the spin axis. That faster precession changes the relationship between Earth's spin dynamics and the frequencies present in the solar system's orbital architecture. In practical terms, it makes Earth's obliquity more stable over long spans than it would likely be without a large moon. This does not mean the tilt is perfectly fixed. It changes within a limited range even now, varying by modest amounts over tens of thousands of years. But those variations are comparatively restrained. Earth does not appear to wander through the kind of extreme obliquity swings that are thought possible for a moonless Earth under the same broader planetary influences. Mars offers a useful comparison in this respect, not because its story is identical, but because it lacks a large stabilizing moon. Mars has only 2 very small moons, far too small to play the same dynamical role that the Moon plays for Earth. Models of Martian obliquity indicate that its axial tilt can vary much more dramatically over long timescales. Earth is not Mars, and every planetary system has its own detailed history. But the comparison helps clarify the Moon's significance. A large nearby moon changes the spin axis problem. It alters the rate and character of axial precession and helps limit the range through which the tilt tends to move. Scientists describe this role carefully. Observations and dynamical models indicate that the Moon stabilizes Earth's obliquity relative to a case in which Earth has no large moon. That conclusion is strong in broad form. What remains less certain is the exact full range that a moonless Earth would experience under every possible ancient configuration of the solar system. Since the architecture of planetary orbits has itself evolved over deep time, different models can produce somewhat different details. Even so, the central picture remains widely accepted. The Moon does not freeze Earth's tilt into one permanent value, but it helps keep the variation moderate rather than extreme. This moderation has a mechanical origin, not a mystical one. The Moon does not protect Earth by shielding it or by holding the axis in place like a rigid brace. It acts through gravity, distance, and timing. It pulls on Earth's equatorial bulge and thereby changes the rate at which the spinning planet's axis responds to the wider gravitational environment. The stabilizing effect is dynamic. It comes from motion acting on motion. The same moon that raises tides on Earth also helps govern the slow behavior of the planet's tilted spin. The story is therefore one of connected systems. Earth's rotation creates an equatorial bulge. The bulge allows external torques to matter. The moon, by being both massive enough and close enough, contributes strongly to those torques. Those torques produce precession. The precession rate influences whether Earth's obliquity remains within a relatively narrow band or enters much larger long-term swings. At each step, the physics is ordinary celestial mechanics, yet the result is profound. The modern Earth carries a tilt that is neither arbitrary nor perfectly constant. It is a tilted world whose lean changes slowly and within limited bounds, in part because the moon has been present all along as a major partner in the dynamics of the spin axis. In this inner layer of the Earth-Moon relationship, the moon's importance is no longer mainly a matter of visible tides or orbital distance. It is written into the posture of the planet itself. Earth turns with a lean, and that lean remains comparatively steady over long spans because the moon helps regulate the slow, gravitational choreography of the axis. The steadiness is not absolute. The regulation is not simple, but the effect is real. The moon helps Earth keep a durable rotational balance, and in that balance the tilted planet preserves one of the most important features of its long-term physical character. A planet's seasons depend first on how sunlight is distributed across its surface during the year. Earth receives energy from the sun continuously, but that energy is not spread evenly at all times or at all latitudes. Because Earth's axis is tilted, the hemisphere leaning toward the sun receives sunlight at a higher angle and for a longer part of the day, while the opposite hemisphere receives sunlight at a lower angle and for a shorter part of the day. This produces the familiar seasonal contrast between warmer and colder parts of the year. The existence of seasons therefore begins with geometry. The character of seasons over deep time depends on how much that geometry changes. Earth's tilt does change, but within comparatively modest bounds. Over long cycles, the angle increases and decreases by small amounts. At present the variation remains limited, roughly between a little more than 22 degrees and a little less than 25 degrees over a cycle of about 41,000 years. That range is enough to influence climate patterns, the strength of seasons, and the distribution of ice, rainfall, and summer warmth at different latitudes. Yet it is still a restrained variation. The planet does not swing from standing almost upright to leaning at an extreme angle. The moon's stabilizing effect helps keep Earth within this narrower range, and that moderation shapes the seasonal framework of the world. When tilt grows larger, seasonal contrast increases. High latitudes receive more intense summer sunlight because the poleward hemisphere leans more directly toward the sun, and they receive weaker winter sunlight because the same hemisphere later leans farther away. When tilt becomes smaller, the contrast softens. Summers at high latitudes become less intense, and winters become less severe in terms of the angle of received sunlight. Low latitudes respond differently. Since sunlight there is already relatively direct through much of the year, but the global pattern still changes. In this way, even a few degrees of difference in axial tilt can alter how energy is allocated across the planet. The important point is not that Earth's seasons remain identical from age to age. They do not. Geological records show repeated climate shifts driven in part by slow changes in orbit and tilt. Instead, The important point is that those changes occur within a range that preserves long-term regularity. Summer still follows winter. Polar regions still experience strong seasonal light changes. The tropics still remain zones of comparatively steady sunlight. Mid-latitude belts still occupy an intermediate position between those extremes. A stable moon does not create an unchanging climate, but it helps maintain a stable seasonal architecture. Without such moderation, the seasonal system could become far less dependable over geological timescales. If Earth's tilt were able to wander through much larger ranges, the distribution of sunlight would be transformed more radically. High-latitude summers could become much more intense during some eras and much weaker during others. Polar darkness and polar daylight would expand or contract more dramatically. The boundary lines between climatic zones would migrate more severely. Ice sheets, rainfall belts, deserts, and vegetation regions would all be pushed by a stronger and less predictable reorganization of solar heating. In that sense, the Moon's role in stabilizing obliquity also supports continuity in the broad seasonal pattern of the planet. This continuity matters because climate is not only a matter of annual average energy, it is also a matter of timing and contrast. Many physical systems depend on the difference between summer and winter, between longer and shorter days, between stronger and weaker sunlight. Snow and ice accumulate or melt according to seasonal thresholds. Soils freeze and thaw. Monsoon circulations depend on changing seasonal heating between land and sea. Ocean-atmosphere exchanges respond to recurring differences in temperature, wind, and light. If Earth's tilt moved through extreme and irregular swings, these systems would still function in some form, but the background structure guiding them would be more volatile. The Moon does not remove every source of climatic variability. Earth's orbit around the Sun also changes slowly in shape and orientation, and these changes combine with tilt to produce the long pacing associated with glacial and interglacial cycles. Continents shift through plate tectonics. Volcanoes alter atmospheric composition. The carbon cycle changes the trapping of heat. Clouds, ice, and vegetation feed back on the climate system in complicated ways. Seasonal moderation by the Moon exists within this larger network of influences. Still, within that network, obliquity remains fundamental because it governs how strongly the hemispheres lean into and away from sunlight across the year. A more stable tilt also means that the latitudinal pattern of sunlight remains recognizably familiar over immense spans. The equatorial region continues to receive relatively strong and steady solar energy. The poles continue to receive weak annual average sunlight but strong seasonal swings in day length. Middle latitudes continue to occupy the transitional belts, where seasonal contrasts are important, but not absolute. These zones shift and breathe under natural climate cycles, yet the overall geometry does not break apart. The world retains a durable arrangement of thermal regions because the axis does not wander wildly. This does not mean every scientist describes the counterfactual case in exactly the same detail. Models of a moonless Earth can differ depending on the assumed state of the solar system, the time interval examined, and the numerical methods used. Some produce strongly chaotic behavior in obliquity over long times. Others differ in how often or how severely the largest swings occur. What observations and dynamics indicate with greater confidence is the comparative result. Earth, with its present large moon, has much more limited obliquity variation than it likely would without that moon. From the standpoint of seasons, that comparative stability is the key scientific conclusion. Seen at the scale of climate, the Moon's influence is therefore quiet but structural. It helps keep the planets lean within bounds, and those bounds help keep seasonal contrast within bounds. The result is not stillness, it is a moderated rhythm. Summers vary, winters vary, ice advances and retreats, rainfall patterns shift, and long climate cycles continue to unfold. Yet the underlying seasonal design of the planet remains coherent through deep time. Earth keeps returning to a recognizable pattern of hemispheric warming and cooling because its tilt, though not fixed, is comparatively well regulated. In that sense, the Moon helps preserve not a single climate state, but the steadier framework within which Earth's seasons continue to operate. A habitable surface begins with matter in the right state and in the right place. Rock must cool enough to remain solid. Water must exist in liquid form for long stretches rather than only as fleeting vapor or deep ice. The atmosphere must allow temperatures and pressures that do not drive the surface too far toward one extreme. Earth achieves this combination early in its history after the violence of formation subsides. The surface is not calm at once. It passes through heavy bombardment, intense volcanism, high heat flow, and repeated reshaping. Yet over time, stable crust forms, water gathers in long-lived basins, and the planet becomes a world where oceans can persist beneath an atmosphere. In that long transition from early chaos to durable surface conditions, the Moon is not the only cause, but it is one of the steadying influences built into the system. Liquid water is central. Earth lies in the region around the Sun where, under suitable atmospheric conditions, surface water can remain liquid. This favourable solar distance is fundamental, and no moon can replace it. The planet's mass also matters because it helps Earth retain an atmosphere and sustain internal activity over geological time. The chemistry of the atmosphere matters. The cycling of carbon between air, water, rock, and mantle matters. Habitability at the surface is therefore a combined outcome of many interacting factors. The Moon belongs within that combination as a modifier of long-term stability rather than as a single controlling cause. One part of that contribution appears in the behaviour of Earth's rotation. The young Earth spins faster than the modern Earth, producing shorter days and more rapid alternation between daylight and darkness. As tidal interaction with the Moon slowly breaks the spin, the day lengthens. This change is extremely gradual, but over immense spans it alters the tempo at which the surface is heated and cooled. A faster rotation tends to shorten the interval of daytime heating and nighttime cooling at any one place. A slower rotation lengthens that interval. Neither state by itself determines habitability, because atmospheric circulation, ocean heat storage, cloud cover, and land-sea distribution all shape how surface temperature responds. Still, the gradual slowing of Earth's spin is part of the evolving physical setting in which a stable surface climate develops. The more important contribution lies in the steadiness of axial tilt, because the Moon helps limit large long-term swings in Earth's obliquity. The distribution of sunlight across latitude remains comparatively regular over geological time. This does not mean the climate becomes unchanging. Earth continues to pass through warm periods, cold periods, ice ages, and intervals of retreating ice. It means that the underlying seasonal geometry remains bounded. Continents, oceans, and atmospheres respond to recurring patterns of sunlight that vary, but not without limit. A stable range of tilt helps the surface avoid the most extreme reorganizations of solar heating that a more erratic axial history could impose. For a surface world, such moderation matters. Ice sheets, rain belts, monsoons, river systems, and ocean circulation all depend on how sunlight is distributed through the year and across the globe. If the tilt were to vary far more wildly, the boundaries between cold and warm regions could migrate with much greater severity. The seasonal availability of meltwater, the persistence of long-lived lakes, and the balance between snow accumulation and summer thaw could become less dependable over deep time. The moon does not prevent change, but it helps keep change within a more continuous framework. That continuity supports the existence of repeated, enduring surface environments instead of forcing the planet through stronger swings in the basic geometry of climate. Tides also belong to this surface story. By moving seawater through basins, across continental shelves, and into coastal margins, the moon helps keep parts of the hydrosphere in constant motion. On the open ocean, this motion is distributed broadly. Near coasts and in shallow seas, it becomes the powerful organizer of water exchange. Tidal currents stir sediments, renew shallow waters, and redistribute dissolved material. These processes do not create the oceans, but they shape how water behaves within them. On a planet with long coastlines, broad shelves, estuaries, and inland margins connected to the sea, repeated tidal circulation helps produce persistent interfaces between land and water. Such interfaces are physically active without being uniformly destructive. They are zones where water repeatedly enters, withdraws, mixes, deposits, and reworks the surface. The importance of these settings lies in duration. Habitability is not only the ability of a place to host liquid water for a brief interval, it is the ability of environments to remain present, accessible, and repeatedly renewed over long spans. Earth's surface becomes habitable in this stronger sense because oceans endure, continents persist, and the atmosphere remains thick enough to sustain pressure and weather. The moon contributes by helping regulate some of the motions that keep these surface systems from becoming static or wildly erratic. The tidal pulse maintains exchange. The moderated tilt supports a persistent seasonal architecture. The slowing spin changes the tempo of the planet without overturning it. This role should be described carefully. Earth would still be a substantial planet in the habitable region of the Sun without the moon, and some models suggest that such a planet could remain habitable in broad terms. It remains uncertain whether a moonless Earth would necessarily lose surface habitability altogether. Scientific consensus is more cautious than that. What is better supported is the comparative statement. With its large moon, Earth gains a more stable obliquity history and strong tides, and these features likely support a more predictable long-term surface environment than would otherwise exist. The moon strengthens the continuity of conditions rather than creating all habitable conditions from nothing. On the early surface, that continuity may be especially important. Once crust cools enough to support standing water, and once oceans and atmosphere begin to interact over long periods, the planet benefits from regularity. Rain can fall into basins that remain. Shorelines can migrate across terrain that does not vanish immediately. Rivers can link highlands to seas. Minerals can weather, dissolve, and accumulate in recurring patterns. None of this depends on the moon alone, yet the moon helps maintain a planet whose surface cycles are organized rather than arbitrary. A habitable world is not merely warm enough, it is a world where environmental conditions recur and persist. Earth's surface, therefore, becomes livable through a partnership of many physical facts: proper distance from the sun, retention of atmosphere, internal geology, long-lived water, chemical cycling, and relative climatic steadiness. The moon enters this picture as a quiet stabilizer and agitator at once. It stabilizes the axial geometry that governs the broad pattern of sunlight. It agitates the waters that move across the coasts and shelves. It helps lengthen the day across deep time through tidal breaking. taken together. These effects do not explain every aspect of Earth's surface habitability, but they form part of the reason the planet develops not just fleeting clement moments, but sustained habitable conditions. Life on Earth does not exist on a motionless surface. It develops and persists within repeating patterns of light, darkness, immersion, exposure, warming, cooling, flooding, draining, stirring, and stillness. Some of these patterns come from Earth's rotation. Some come from Earth's orbit around the Sun. Some come from the Moon's gravitational pull on the planet's waters, and from the Moon's changing position in the sky. Together they create a world in which time is not abstract. Time is built into the environment itself. It arrives as dawn and night, as high tide and low tide, as spring tide and neap tide, as the waxing and waning brightness of the moon. Living systems do not merely endure these cycles. Over immense spans, they adapt to them. The most general rhythm is the daily cycle of light and darkness. Because Earth turns, the surface passes repeatedly into sunlight and out again. This gives living organisms a dependable alternation between day and night. Many forms of life possess internal timing systems, often called biological clocks. A biological clock is a built-in process that helps an organism keep track of regular environmental cycles, even when immediate conditions change. In plants, microbes, animals, and fungi, such clocks coordinate activity with the expected pattern of light and dark. Leaves open and close, photosynthetic activity rises and falls, hormones, metabolism, rest, feeding, and movement follow roughly daily timing. The planet's rotation provides the basic cadence, but that cadence has been slowly changing through Earth's history as the day lengthens. Even as the day length changes across geological time, the larger principle remains constant. Earth remains a world of repeated daily alternation rather than permanent daylight or permanent darkness over most of its surface. This regularity matters for life because it allows physiological processes to evolve in relation to predictable intervals. Organisms can prepare for change rather than simply react after it arrives. In a world where the daily pattern is repeated with great reliability, selection can favor timing as well as structure. Life becomes rhythmic because the environment is rhythmic. Near the coasts, the moon adds another layer. Tides bring water in and carry it out. They cover mudflats and expose them again. They refill tidal pools and isolate them later. They bathe roots, stems, rocks, and sediments in seawater, then leave them in air and sunlight until the next return. Organisms living in these places encounter a world defined not only by one daily cycle, but by overlapping cycles of day and tide. Some are submerged during one part of the tide and exposed during another. Some feed only when currents are strong. Some release eggs, sperm, or larvae at times that increase the chance of dispersal or survival. Some retreat into burrows or close their shells as the water falls away. These are not random behaviors. They are adjustments to a clock carried in the sea. The intertidal zone offers one of the clearest examples. This zone lies between the typical high water line and the typical low water line. It is not fully marine and not fully terrestrial. It alternates between the two. A rock in this band may sit underwater for part of the day and in open air for another part. A patch of sediment may be cooled by the sea on one tide, warmed by the sun on the next exposure, and crossed again by moving water a few hours later. Organisms living here must tolerate repeated change in moisture, temperature, salinity, oxygen, and mechanical force. The moon's tidal rhythm therefore imposes a demanding but dependable schedule. Life in such places often becomes highly specialized because survival depends on matching behavior and physiology to repeated immersion and exposure. Scientists describe some of these patterns with terms such as circadian, circalunar, and circatidal rhythms. Circadian refers to an approximately daily cycle. Circalunar refers to a cycle linked to the lunar month. Circatidal refers to a cycle linked to the tides. These rhythms can be observed in many organisms, especially in marine and coastal settings. Crabs may become active at particular tidal phases. Some worms and fish coordinate reproduction with the lunar cycle. Corals on certain reefs can release reproductive material in striking synchrony associated with seasonal and lunar timing. Grunion on some Pacific coasts come ashore to spawn during particular high tides. These examples differ in detail and in mechanism, but they show the same broad truth. Life can become tuned not only to the sun's light, but also to the moon's tidal and monthly patterns. This tuning does not imply conscious awareness of celestial motion. It arises through evolution and physiology. Organisms with timing systems better matched to stable environmental cycles often feed more efficiently, avoid danger more effectively, reproduce more successfully, or conserve energy more reliably than organisms whose timing is poorly matched. Over many generations, traits that align life processes with recurring external patterns can therefore be favored. The result is a living world in which behavior, growth, and reproduction are often scheduled by physical cycles older than life itself. The value of such rhythms lies partly in prediction. A tide returns. Darkness follows daylight. Spring tides recur after neap tides. Seasonal light patterns repeat. For a living system, a predictable environment is not a static environment. It is an environment in which change comes in expected forms. That distinction matters. Repeated change can be used. Organisms can time feeding to the arrival of currents carrying suspended food. They can time emergence to the coolness of night rather than the heat of day. They can time spawning to stronger tidal exchange or to phases of moonlight that alter predation and dispersal. The physical world provides the schedule, and living systems grow into it. These repeating patterns also structure habitats over long times. Tidal marshes, mangrove margins, mudflats, shallow lagoons, rocky shelves, estuaries, and reef flats are not merely places on a map. They are environments defined by recurrent timing, their chemistry, sediment movement, oxygen conditions, and water depths all oscillate. Organisms living there often form communities whose composition reflects the timing regime as much as the material substrate. One height on a shore may be wet often enough for one assemblage and dry often enough to exclude another. A channel flush strongly on spring tides may differ biologically from a sheltered pool that turns over more slowly. The moon's rhythm becomes part of the architecture of habitat itself. On a broader scale, the coexistence of daily solar cycles and lunar tidal cycles enriches the temporal texture of Earth's surface. Life does not develop under one simple clock but under several interacting clocks. The daily cycle organizes photosynthesis, rest, and temperature response. The tidal cycle organizes immersion, current, transport, and coastal foraging. The lunar month modulates the strength of tides and the level of night illumination. Seasonal changes alter the background conditions in which all the shorter rhythms operate. This layered regularity gives Earth a distinctive pattern-rich environment. It is neither unchanging nor chaotic. It is structured in time. For living worlds, such structure matters deeply. It allows persistence through repetition. It allows adaptation not just to places, but to intervals. Earth's surface becomes not only a set of spaces where life can exist, but a set of rhythms within which life can organize itself. The moon, through the tides and through monthly change, becomes one of the quiet authors of that organization. It helps turn physical recurrence into biological pattern, and biological pattern into long continuity across the living surface of the planet. At the innermost level of this story, the moon's departure is not a simple loss. It is part of a long balancing process within the Earth-Moon system, a process that changes the planet while preserving the conditions that allow a living surface to endure. The moon moves away, but it does so because the connection between the two bodies remains active. Gravity continues to link them. Tides continue to transfer motion from Earth's spin into the moon's orbit. Earth continues to slow. The orbit continues to widen. These changes unfold so gradually that they seem motionless within ordinary life. Yet across deep time they shape the physical character of the planet. The moon is leaving, but it is leaving through relationship, not through abandonment. That distinction matters. A weaker bond would imply disorder or escape. The real process is more structured than that. The moon remains firmly bound to Earth while the system redistributes angular momentum and dissipates energy. Nothing in this exchange is abrupt. The ocean rises and falls. The solid Earth flexes. The atmosphere shifts. Friction within these moving parts turns a small portion of organized motion into heat. The rest is carried into a larger orbit for the moon and a slower rotation for Earth. The receding moon is therefore not evidence that the system is coming apart in any immediate sense. It is evidence that the system is evolving according to stable physical rules. Within that evolution, Earth gains a remarkable combination of traits. Its rotation slows from the faster pace of youth toward the more moderate pace of the present. Its axial tilt remains comparatively well regulated, because the moon helps govern the long-term dynamics of the spin axis. Its oceans move under strong and repeated tides that stir shelves, coasts, and estuaries. Its surface conditions remain variable, but variable within bounds that support continuity rather than permanent upheaval. These outcomes are not separate gifts delivered independently. They're connected expressions of one long gravitational partnership. This is why the central idea is more subtle than the statement that the moon makes life possible by itself. Earth's habitability does not arise from one cause alone. It depends on the planet's distance from the sun, its mass, its atmosphere, its liquid water, its internal geology, and the chemical cycles that keep surface conditions from running too far toward heat or cold. The moon does not replace any of those factors. What it does is help shape the stability, rhythm, and pacing of the system within which those other factors operate. It is not the entire reason Earth can sustain a habitable surface. It is part of the reason Earth can sustain that surface so steadily over immense spans. The phrase that the moon is leaving Earth can therefore mislead if it suggests a future in which the moon simply slips away and the present world suddenly fails. The actual recession is measured in centimeters per year. Over human timescales, it is negligible. Over geological timescales, it matters greatly, but even then it is part of a slow continuum rather than a sudden break. The moon was once much closer. Earth once rotated much faster. The tides were stronger. The length of the day was shorter. Since then, the system has been adjusting step by step. The present Earth is one stage in that long adjustment, not the fixed goal toward which all earlier history moves and not the final state beyond which nothing remains. What makes this stage so important is its balance. The moon is large enough and close enough to exert strong tidal influence, yet distant enough that the system is not dominated by extreme tidal forcing of the kind that would accompany a much nearer moon. Earth rotates neither at the furious pace of its youth, nor at the slower pace of a far future state. The axial tilt varies, but within moderate limits. The ocean is active, yet not continually overwhelmed by tidal extremes. In this sense, Earth inhabits a dynamically tempered condition. The Moon's slow retreat is part of how that condition emerges. There is a deeper lesson in this. Habitable worlds are often imagined in static terms, as though the right planet simply appears with the right ingredients and remains suitable because those ingredients stay in place. The Earth-Moon system shows a different picture. Suitability can arise within motion. Stability can be the product of ongoing change rather than the absence of change. The Moon does not help Earth by freezing it into one state. It helps by participating in a long evolution that moderates some extremes, sustains repeated environmental rhythms, and links daily experience at the surface to celestial mechanics far beyond the atmosphere. Even the fact of recession contributes to this lesson. If the Moon did not interact tidally with Earth, it would not be moving outward in this way. The same process that carries it away is the process that slows Earth's rotation and reflects the exchange of motion through tides. The departure and the benefit are therefore aspects of one mechanism. The Moon is not valuable despite leaving. It is valuable in part because its leaving records the active physical coupling that has helped shape Earth's long-term environment. This does not make the Earth-Moon system perfect or permanent in any absolute sense. Planetary systems continue to evolve. The Sun itself changes over time. Continents drift, atmospheres transform, oceans open and close. The Moon's recession rate is not constant across all ages, because the arrangement of seas and continents changes the efficiency of tidal dissipation. The future of Earth depends on many processes larger than the Moon alone. Yet within the long span of time during which Earth sustains a temperate surface and a living biosphere, the Moon remains one of the quiet structural influences that help make such continuity possible. So the innermost truth is not only that the Moon moves away, it is that Earth and Moon have been shaping one another ever since the system begins. The Moon's orbit widens because Earth turns. Earth's day lengthens because the Moon raises tides. Earth's axial behavior remains comparatively steady because the Moon pulls on the planet's equatorial bulge. Ocean waters continue their regular motion because the Moon's gravity varies across the planet. Life inherits a world of repeated rhythms because these motions persist. The Moon leaves slowly, and in leaving slowly it helps define the balanced world from which it is receding. Earth remains habitable not through stillness, but through an enduring partnership written in motion, distance, gravity, and time. Night settles over the planet in the same patient way it has settled for ages, while Earth continues to turn and the Moon continues its slow outward path. Nothing in that motion feels hurried. The sea still rises and falls, the coasts still flood and empty. Light still returns each morning, and darkness still follows. Beneath these familiar changes, the deeper exchange continues without pause. Earth gives a little of its spin. The Moon carries that gift into a wider orbit. The bond remains active precisely because the distance is changing. From far away, the Earth-Moon pair appears calm. From within, it is full of quiet adjustment. The axis holds its long, leaning posture. The oceans keep their measured pulse. The surface remains a place where water can gather, climates can persist, and living things can adapt to repeated patterns instead of constant upheaval. The Moon does not create this world alone, yet it helps steady its rhythms and shape its long continuity. So the story comes to rest in a simple truth. A habitable planet is not only a place with the right ingredients, It is also a place with the right long motions. Earth is such a place in part because it has never been entirely by itself. Its companion is small beside it, dark beside it, silent beside it, yet always involved. The moon moves away by centimetres, while its influence remains written into the length of the day, the reach of the tide, the steadiness of the seasons, and the enduring balance of the planet. The sky above Earth therefore holds not only a familiar light, but a record of a partnership still unfolding. The moon recedes, Earth turns, the oceans answer, and the living surface continues beneath them both, held within a slow celestial relationship that has never truly stood still.